Section 2.4, the title is The General Solution to the Wave Equation is a Superposition of Normal Modes. So we already discussed the normal mode, right, in the last lecture. So we want to obtain the general solution for the wave equation, and the title says that that should be the superposition of normal mode. So we have successfully found that spatial function, capital X, and now we are going to attach the subscript n to explicitly denote that this spatial motion is spatial motion is quantized. So this is the standing wave shapes of the stream. So now we need to describe how these shapes oscillate in time. That means we have to solve the temporal part, so time-dependent differential equation. So you might remember that we were using the separation of variables, and we employ the separation constant, right? Separation constant K. In the last lecture, we discussed the possibility of K. So which value should be used for this? Positive K? No, right? So we have to enforce the K should be less than 0. So negative K can give only the effective oscillation motion. So to explicitly denote that the capital K is negative value, so we put something like that. And from the spatial motion, we know that the K should have some form like n pi over L. So with this explicit value for capital K, or the separation constant K, we can solve the temporal part of the partial differential equation. So temporal part should look like something like this, right? So if we introduce this explicit value for capital K, then that means m pi over L square v square t equal 0. So this ordinary differential equation might look very complicated because of the weird coefficient here. But in essence, this is simply the second order ordinary differential equation. So you just want to find the some function capital T that can give the same shape as the original its function T with some constant value. So we have already met this type of ordinary differential equation when we solve the spatial part, right? So candidate for the capital T should have some like trigonometric function type, or it should be exponential function type, right? So we want to differentiate temporal T 2 times, but still we still want to the second derivative has the exactly the same form as its original function. So we can try the exponential function and the cosine function. And from our understanding from the spatial part, we can write that the temporal part solution should look like dn So the reason why we put the subscript n for here is trivial. As we discussed in the spatial part solution, we already know that with this coefficient should be discrete values, not the continuous value, right? So that's why we have n here. And we also know that this ordinary differential equation is linear equation. That means if you have more than one solution, then their linear combination can be also solution to this problem. So that's why we have both cosine and sine function here. And this omega value, this is the angular frequency for the harmonic oscillation motion. So for the specific mode n, so this value should be given as n pi v over L. So you can recognize where this omega value comes from, right? So this coefficient, where I denote with star. So simply this value is angular frequency omega. So now we have the solution for spatial part, the capital X, and we have a solution for the temporal part, the capital T. So now we want to combine the spatial part and temporal part to make the general and whole solution to the one-dimensional wave equation. So let's combine them. That means x and x, t and t. So this is simply just fn cosine So temporal part is contains both sine and cosine function, and we have only sine function for the spatial part. And you might realize that the coefficient before the cosine and sine function is changed, f and gn, from dn and en. So that's because of some coefficient for the spatial part. So spatial part also has some coefficients, right? So we want to combine the coefficients from the spatial part and the temporal part. And now we define the new arbitrary constant or coefficient, fn and gn. So I hope that this doesn't confuse you. So the whole solution now will be denoted as the displacement function. And now displacement function also needs to be indexed with n. So this is called normal mode. So normal mode might sound like some strange word, but this is simply the solution to your one-dimensional wave equation. And we are going to learn a little bit more terminology to discuss the normal mode. So interestingly, each of these modes corresponding to a specific integer n has a special name. So I don't know why scientists want to name such weird. They want to give some weird name what they found. So we don't just say n equal 1 mode. So for n equal 1 mode, the name is the fundamental mode. N equal 1. So this is the simplest mode of vibration. And it has the lowest frequency. So the frequency omega n is defined as n pi b over L. So for a given string, the length L and the velocity b is fixed value. So n can be a single variable. So with the with the lowest value for among the allowed values, so n equal 1 should be the smallest value. So it has the lowest frequency. And this mode is also known as the first harmonic. So simply you can just remember that this mode is the first motion to describe the harmonic oscillation. So that's why we have the first here. And you can easily imagine that the name for the n equal 2 mode. So n equal 1 is the first harmonic, then n equal 2 should be second harmonic. And the weird thing is the n equal 2 mode has also different terminology. So we have the terminology overtone. So n equal 1 is the first overtone. So n equal 1 is the fundamental and ground mode, and n equal 2 is one level above than the fundamental mode. So that's why it has the name the first overtone. Overtone means like the higher excited states. So this is the first excited state mean. So in this terminology, you can easily imagine that nth vibration mode has the name of the nth harmonic and n-1's overtone. So this unique sound of the musical instrument is determined by the specific mixture and the intensity of these different harmonics. So when you pull the strings of the guitar or violin, then many of these normal modes are beginning to contribute, and that makes some beautiful or some ugly sounds. Okay, then let's move on to the next page. So now so the crucial property of wave equation is that equation is linear, right? I emphasized this property so many times in this lecture. So ordinary differential equation, the one-dimensional wave equation is a linear equation. That means the sum of any number of valid solution is also a valid solution. So this is known as the principle of superposition. So I guess you have heard this terminology, superposition, so many times in this day, because nowadays like every countries like South Korea, United States, China, and they are all about they want to take the lead of the quantum information science. And the superposition is one of the main characteristics of quantum information science. So in classical mechanics and classical physics, the superposition is not allowed. That means you cannot be here and you cannot be there. Like you cannot be simultaneously here and there. Right? In classical physics, you have to be here. That means you are not. If you are here, then you cannot be there. But in quantum mechanics, it is possible. So you can be here and you can be there. So that is the superposition of quantum mechanics. So our general solution to one-dimensional wave equation also the superposition of allowed normal modes. So we write down the single mode specific to normal mode n should be written like this. So let's imagine that U1, this can be a solution to one-dimensional wave equation. U2, this also can be a solution to one-dimensional wave equation. So in this way, you can write down like nearly infinite number of allowed solution, like U100, XT is also allowed solution. So if you have more than single valid solution, the real general solution should be the linear combination of all of them. And do we have a limit for n? Yes, we have. So we know that the n should be larger than 1 and n should be the integer value. But do we have a higher limit, higher boundness? No, right? So this value can go infinity. So our general solution also should be the infinite sum of specific normal mode. So we are going to take the sum from n equal 1 to n equal infinite values. This will be your general solution for the displacement. So this result means that the most general motion of the string is not a single motion of harmonics. So it is not so the general solution cannot be usually the sum of many of the specific normal mode motions. So this is the result of superposition. So the general solution is the sum of many of valid solution. So this powerful equation tells us that any possible motion of the string, vibrating string, no matter how complex the initial shape, so we can just perfectly describe the motion of displacement using infinite number of specific normal mode. Then you might want to ask, what about Fn and Gn? So they are just random arbitrary numbers which appears during the solving differential equation. So how can we determine these two values? So in solving differential equation, we always have to remember that so we are not solving, we don't want the solution to general problem. So we want a solution for a specific problem that we want to solve, right? for our case, we want to solve the vibration motion of string with length L. So we always have some boundary condition for our specific problems. So if you want to determine two coefficients, then you can apply the boundary condition. And you also have to think about the initial condition. So we haven't discussed this. But this is simply the boundary condition for like the version of boundary condition for temporal part. So for the temporal part, there is no actually boundary, right? So boundary is the terminology for the territory or some land or space discussion. So the boundary condition for the temporal part, it might sound a little bit weird. So we use the different terminology. So initial condition. So for the time part or temporal part, the initial and the final sounds much more natural, right? So that's why we use the initial condition for the temporal part. So you have a boundary condition and initial condition to determine these two values. So that's whole determines your vertical displacement of string. So now we are going to discuss time evolution. So still we haven't discussed how this general solution can describe the time evolution of the string. So if you imagine the string something like this motion, and after time the string will have the shape something like this. Or you want to describe the transverse motion of wave. So do you think that it is possible to describe such motions using this general solution? So the answer is yes. So we are not going to discuss how we can determine which specific mode contributes to each motion, but in principle we can do this. I guess you already learned the Fourier transform in the mathematics class, right? So in that class tells you that any weird shape motion also can be described by the known function. So no matter how the shape of the function look weird, if we have many sine or cosine function, then we can expand that weird function too. So with the general solution uxt, so the combination of the specific mode can create the pattern like the appearing to move, which is how a traveling wave can be expressed as a consequence of superposition of standing waves. So for example, like if we want to describe this shape, then there is no single mode that can describe this motion. But if we have like this motion and this motion, and something like this motion. If you add many more functions, then this part will be cancelled out. And this part also will be cancelled out. But it is actually, this is not a good example, but I guess you can imagine that if we add up many functions, then we can generate this shape too, this weird shape. So I have to prepare some examples, but I think I can do this in the class time, but actually it is not working. So I guess the best way to check this time evolution is the picture in the textbook. So that perfectly describes the traveling motion of the standing wave using two specific mode. So you can refer to that. Okay, let's move on to next page. Section 2.5. So section 2.5 is, now we want to describe the vibrating membrane, which is the two-dimensional analogy of single string. So vibrating membrane, the motion of vibrating membrane is described by two-dimensional wave equation. So this is a very natural and simple extension from one-dimensional problem to two-dimensional problem. So we want to set up the two-dimensional problem first, two-dimensional problems. So the vertical displacement of the membrane is given by a function of u, which contains three variables, x, y, and t. So in addition to x and t, now we, in the one-dimensional vibrating motion, we have one more variable, y. Because now we are dealing with two-dimensional vibrating membrane. That means, so our membrane should look like this. So if you want to specify the position on the two-dimensional membrane, you need two coordinates, x and y. So that's why there is additional variable for spatial part. And the governing equation is the two-dimensional wave equation. So this is the simple extension of one-dimensional wave equation. So it looks very similar to the one-dimensional wave equation. So we will consider a rectangular membrane of size A by B, clamped along the entire parameter. So we assume that this parameter of rectangular, it should be fixed at 0 point. So this gives us the boundary conditions that the displacement u must be 0 along all four edges for all time. So that means the displacement u of x equals 0, y, t, this should be 0, right? that describes the x equal 0. And there are 3 more additional boundary conditions. So u equal for u, x equal a, y can be any value, and time can be any instant. And this also should be 0. So this equation means that this part should be 0. Then you can write down two additional boundary conditions. So we have written the 4 boundary conditions. And now we set up the problems. The next step should be the separation of variables. So we can apply the separation of variables because the variables are all independent to each other. So that means we can vary x without any impact on y and t values, right? So you can fix the position of y here, and you can move on the x-axis, along the x-axis, right? So x is actually independent variable, and y is also independent variable, and time is totally different characteristic compared to other 2 spatial parameters or variables, x and y. So u, x, y, t, you can factor the spatial part and temporal part first. F, x, y, and time t. And you can easily imagine that the spatial part is also further breakdown. So x, x, y, y, t, t. So that means we apply the separation of variables twice. So for the first time, we want to separate the spatial part and temporal part. And the second application of separation of variables allows us to separate the x and y motion. So with this result, we are going to put the displacement function in the 2-dimensional wave equation. Then that gives you 3 ordinary differential equation. And the last equation for the temporal part. So the way to solve these 3 ordinary differential equations are exactly the same as we discussed for the 1-dimensional wave equation. So you can solve the spatial part first, then that will give you the quantization along the x and y motion. That means not all the values are allowed for p and q. So p and q should be quantized, which means the p and q are discrete values. So that also has an impact on the temporal motion because P and Q are quantized values, so the temporal part is also quantized. So this is simply just a tedious mathematical job, so I think you can practice by yourself. And we can just check the result of these solutions. So you can easily imagine that for spatial part x, capital X, that should be the sine function and pi x over a. For the y-axis motion, so you might notice that we have used different quantum number n and m because the x and y are independent variables. So there should be, it doesn't have to have the same quantum number for x and y motion. So that's why we have two different quantum number notation. But the restriction for the quantum number is quite same. So for n should be the positive integer, larger or equal to 1. M has the same restriction. Okay, so far nothing new and very easy to understand and follow. But there is some unique characteristics of the vibrating membrane compared to one-dimensional problem. So that to discuss that, we are going to write down the angular frequency. So angular frequency now depends on two quantum numbers, n and m, because as you can see in the temporal ordinary differential equation, T contains both P and Q. That means the temporal part is dependent on both n and m. So the final value should sorry. So now I want to discuss the degeneracy. So let's imagine that we have a rectangular shape that has both sides have an equal length. So let's imagine that the case A equal B. So a fascinating and important phenomena called degeneracy arises when the system has some symmetry. So that we enforce the symmetry using the same length of both sides. So in this square membrane, angular frequency now becomes something like this. So now let's compare two different modes, 1 and 2 mode, and 2 and 1 mode. So the angular frequency for each mode, omega 1, 2 and omega 2, 1, you might easily realize that their values should be same, right? Because now we are plugging in n equal 1 and m equal 2 for omega 1, 2. if you want to calculate omega 2 1, then you might want to plug in 2 for n and m 1 for m. So even though there is some like exchange, the values for n and m, but still their sum should be same, right? So for the addition, the sequence of addition is not important. So 1 plus 2 and 2 plus 1 should be equal, both equal to 3, right? So similarly for this case, their angular frequency should be a over b pi, sorry, why square here? b pi over a root pi. So they have the same angular frequency. And that leads to the same energy too. But do they look like same? Well, actually it is not, right? So for omega 1, 2, the motion corresponding to omega 1, 2 has one node along the x-axis and two nodes for the y-axis. But what about omega 2, 1? It has two nodes and one node along the y-axis. So shape is totally different. So this, although the solutions have the different shape, but they correspond to the same energies, then this is known as the degeneracy. So actually this is a very common and well-known concept in general chemistry. So you already know that orbital P, atomic orbital P has 3 degeneracy. So P plus 1, P0, and P minus 1. So this is the result of the degeneracy. And you already know that you already apply the linear combination. So you usually learn the p orbital that they are consisting of px, py, and pg. But when you solve the Schrödinger equation for atomic hydrogen, you will obtain these 3 orbitals. But you will realize that maybe in chapter 5 or 6, they contain 2 of them contains imaginary part that makes the difficult to visualize on real space. So we are going to utilize linear combination. So we have emphasized this term, this characteristic too many times, I guess. So if we have a valid solution, then their linear combination also be a valid solution to our problem. So using linear combination, we want to remove the imaginary part. So all of them now are real functions, and they are aligned x, y, and z axis. So even though you might not really notice that we are discussing the degeneracy and the linear combination characteristics of partial differential equation of our problem, but you already use this concept and you are very familiar with this concept too. So in this chapter, we discussed that explicitly. So I guess that's it for the chapter 2. So even we have section 2.6 that is much more oriented to physics class, and they talk about the interference. So I'm not going to discuss that one in our lecture, but yeah, if you really want to understand quantum chemistry, then I strongly recommend you to read by yourself. So let's summarize what we have learned together in the chapter 2. So there are some keywords that we have learned: the classical wave equation. So moving from the single one-dimensional vibrating string to the more complex two-dimensional vibrating membranes. So to solve the classical wave equation, we apply the separation of variables. So this successfully transforms the single partial differential equation into a set of solvable ordinary differential equations. So during our mathematical journey, we have met 3 very important physical principles. The first is quantization. So we saw how the simple physical constraint of fixing the ends of a string or the edges of 4 edges of a membrane that lead to the quantization of the solution. So string motion is quantized and the vibration motion of the membrane is also quantized. So a discrete set of solution that is called normal modes. And the second important concept is superposition. So the linearity of the wave equation allowed us to construct any complex motion as a sum or as a superposition of the normal modes, right? So general motion of one-dimensional string is the infinite sum of the normal mode. And the last thing is degeneracy, just we discussed. So when we extend our analysis from 1 dimension to 2 dimension, we have met the degeneracy. So when the solutions are physically different, which means they have different shape, they can correspond to the same energy. So this phenomena is known as the degeneracy. So, yep, that's it for us today. And with this background, we can solve the Schrödinger equation in chapter 3. So, yeah, we don't have many things to discuss today, so I guess we can call it a day a little bit earlier today. That's nice, right? Okay, let's meet next Monday. So I will say